In late 2023, a quiet paper circulated through astrophysics departments following observations from the James Webb Space Telescope. While analyzing infrared data from distant stellar systems, researchers noted energy distributions that did not match known stellar behavior, planetary reflection, or dust dynamics. The signal was weak, statistically cautious, and deliberately described as unexplained rather than extraordinary. Still, it triggered internal discussion because it resembled patterns previously theorized but never observed. Patterns associated not with nature as we know it, but with deliberate structure. At the same time, a separate team working with data from the Gaia Space Observatory reported inconsistencies in stellar motion across several regions of the Milky Way. These stars were not behaving chaotically, nor following clean gravitational models. Instead, they showed subtle coherence, as if influenced by something massive yet distributed. No single anomaly would have raised concern on its own. Together, they forced scientists to pause and compare notes. What made these findings unsettling was not their drama, but their restraint. There was no declaration of discovery, no press conference announcing contact, no claim of intelligence. Instead, there was a shared discomfort in how familiar explanations failed to fully account for what was being measured. The data sat in an uneasy space between noise and meaning. That ambiguity is precisely what science takes most seriously. For decades, the search for advanced civilizations has focused outward, scanning for radio signals, laser bursts, or obvious megastructures. But these recent observations did not announce themselves. They blended into background data, visible only when researchers stopped asking whether something was communicating and started asking whether something was operating. That shift in perspective has changed the nature of the question entirely. Scientists are now facing a possibility they once treated as purely theoretical. Not that an advanced civilization might appear one day, but that one may already exist, operating in ways that do not resemble our expectations of technology or presence. The central mystery is no longer where to look, but whether we have misunderstood what we are looking for at all. One of the oldest tools scientists use to discuss advanced civilizations is known as the Kardashev scale. Proposed in the 1960s, it does not measure intelligence through language or biology, but through energy use. The idea is simple in structure and ambitious in implication. A civilization's level is defined by how much power it can access and control. Not what it thinks, but what it can physically command. At the lowest level, a civilization uses the energy available on its home planet. Humanity currently resides here, drawing power from fossil fuels, sunlight, wind, and nuclear reactions. This level reflects technological coordination more than wisdom or intent. It describes capacity, not purpose. Even so, it took our species thousands of years to reach this stage. The next theoretical level involves harnessing the full energy output of a star. This does not imply domination, but efficiency on a scale that dwarfs planetary concerns. Concepts like stellar collectors or orbital energy networks are often used as illustrations. They remain speculative, but not forbidden by physics. Importantly, such structures would alter how a star appears to distant observers. Beyond that lies a level defined by control over an entire galaxy's energy. At this scale, individual planets or stars lose relevance. The civilization becomes interwoven with large-scale cosmic processes. Motion, radiation, and structure could all be influenced indirectly. Detecting such a presence would be less about seeing machines and more about noticing patterns that persist across vast distances. What makes this framework useful is not its predictions, but its constraints. It forces scientists to think in terms of thermodynamics and observables. Any advanced activity must leave a footprint in energy flow. Heat must go somewhere. Motion must obey conservation laws. These requirements allow speculation without abandoning rigor. However, the Kardashev scale also carries an assumption that now feels increasingly fragile. It assumes that advancement always correlates with greater and more obvious energy use, more power, more visibility, more structure, more detectable waste. This linear progression mirrors human industrial history, not necessarily universal behavior. As researchers revisit the scale today, they are asking whether it measures advancement or merely expansion. A civilization focused on efficiency, stability, or information might reduce its visible footprint rather than enlarge it. It could operate closer to equilibrium, not excess. In that case, higher advancement would mean quieter signatures, not louder ones. This reframing places humanity in an uncomfortable position, not at the bottom of a ladder waiting to climb, but possibly standing beside a blind spot in our own definitions. If intelligence can grow while becoming less energetically conspicuous, then the framework itself may already hint at something unsettling. That advanced presence might not announce itself through power, but through absence. In 2015, astronomers studying data from the Kepler Space Telescope noticed a star behaving in ways that defied easy explanation. Its brightness dropped irregularly, sometimes sharply, without the periodic rhythm expected from orbiting planets. The variations lacked symmetry and consistency. Natural explanations were proposed, revised, and questioned. What remained was not a conclusion, but a lingering anomaly. Similar moments have appeared across different branches of observation. Fast radio bursts, for example, arrive as intense pulses from distant galaxies, lasting only milliseconds. Many have since been linked to extreme astrophysical events, such as magnetars. Yet a small subset displays repeating patterns that strain current models. Scientists do not claim intention, only that the behavior challenges comfortable categorization. Infrared surveys have produced their own puzzles. When researchers search for excess heat around stars, they expect it to come from dust or early planetary formation. In rare cases, however, the thermal profiles do not align with known distributions. The energy seems organized rather than diffuse. Not artificial, but not easily natural either. Gravitational data has also contributed to this unease. Certain stellar groupings move with coherence that suggests long-range influence beyond visible mass. Dark matter is often invoked, and for good reason. Yet models remain incomplete, and some motions resist refinement even when dark matter is carefully accounted for. The equations balance, but the intuition does not. What unites these cases is not their strangeness, but their persistence. Each anomaly survives repeated scrutiny without collapsing into error or clear explanation. They are not dramatic enough to announce discoveries, but too consistent to ignore. Scientists often describe them as uncomfortable data, observations that refuse to disappear. Importantly, none of these signals point cleanly to technology. They do not resemble broadcast structures or propulsion. They lack signatures we have learned to associate with engineering. That absence has historically been used to dismiss them as irrelevant to the search for intelligence, but absence itself can be misleading. Modern science is shaped by what it expects to find. Instruments are tuned to known phenomena. Filters remove what appears unimportant. When data resists interpretation, it is often sidelined rather than recontextualized. This process is practical, but it carries a hidden cost. It assumes the unknown will resemble the known, only slightly altered. As more anomalies accumulate, some researchers are reconsidering that assumption. The problem may not lie in the data, but in the framework applied to it. If advanced activity does not mirror our technological trajectory, then detection methods based on that trajectory may be insufficient. In that case, the universe may already be signaling, just not in a language we recognize. When scientists allow themselves to step beyond conventional interpretations, the same observations begin to suggest broader possibilities. This does not require abandoning physics, only relaxing assumptions about scale and intent. Instead of asking whether a signal was designed to be seen, researchers begin to ask whether it was designed at all. The distinction subtly shifts the scope of inquiry. Advanced systems, whether biological or technological, often evolve toward efficiency rather than visibility. In nature, the most stable processes are frequently the quietest. They persist because they waste little energy and leave minimal disruption. If a civilization followed a similar trajectory, its influence might manifest as regulation rather than expansion. Theoretical models of post-industrial advancement explore this idea cautiously. Some suggest that sufficiently advanced intelligence would prioritize internal optimization over outward growth. Computation, simulation, or information processing could replace physical infrastructure. In such scenarios, energy use does not disappear, but becomes tightly controlled and locally balanced. From a distant perspective, this would be nearly invisible. Waste heat could be dissipated at background levels. Large structures might be unnecessary, replaced by distributed systems operating near physical limits. To an external observer, the region would appear unusually calm, not busy. Order would resemble emptiness. This challenges one of the foundational expectations in the search for intelligence. We look for excess, for deviation, for noise. But an advanced system optimized for longevity might produce the opposite. Its signature would be a lack of disturbance, stability where chaos is expected. Some researchers have begun exploring whether certain cosmic regions show this kind of unnatural regularity. Areas with lower than expected entropy growth, or systems that appear unusually well regulated over time. These studies remain speculative and controversial, yet they are grounded in measurable properties. Another boundary is crossed when time itself enters the discussion. Long-lived systems must manage not only energy, but change. Over cosmic timescales, even small instabilities accumulate. Maintaining coherence would require predictive models far beyond human capability. Such control would not announce itself, but it would shape outcomes subtly. At this level, the question shifts again. Detection becomes less about spotting artifacts and more about recognizing influence. Not a beacon, but a bias. Not a structure, but a tendency. The escalation is not toward fantasy, but toward a quieter form of plausibility. If this line of reasoning holds, then the absence of obvious signs may no longer be reassuring. It may instead indicate that detection methods are tuned to the wrong scale of advancement. In that case, the universe could already host systems operating beyond our observational horizon, not because they are distant, but because they are refined. As speculation moves beyond raw power, attention turns toward control over underlying systems. Energy alone does not define capability. The way energy is shaped, delayed, redirected, or encoded may matter far more. At extreme levels of advancement, influence over reality could emerge not through force, but through precision. Physics already hints at this possibility. Information is now understood as a physical quantity, tied to entropy, computation, and state change. Manipulating information at fundamental levels could alter outcomes without obvious expenditure. A system optimized around information control might leave almost no energetic trace at all. Time becomes relevant here, not as science fiction, but as a variable to be managed. Even without reversing time, predicting and shaping future states can mimic control over causality. Advanced forecasting allows intervention before disruption occurs. From the outside, events would appear natural, yet improbably well-timed. Space too offers subtle leverage. Small adjustments in gravitational fields, orbital resonances, or energy gradients can compound over long periods. Such interventions would not look like construction or destruction. They would look like patience. A civilization operating at this level would not move mountains. It would let mountains move themselves. These ideas remain theoretical, but they are not ungrounded. Human technology already reflects early versions of this shift. We increasingly favor algorithms over engines, coordination over consumption. Progress has begun to separate from visibility. Extrapolated far enough, advancement may become indistinguishable from natural law. This creates a profound challenge for observation. If manipulation occurs within statistical margins, detection becomes nearly impossible. The system appears unchanged, yet behaves differently than chance would predict. Scientists rely on anomalies to signal intervention. But what if intervention minimizes anomalies by design? Such control would not resemble dominance in any familiar sense. It would not announce authority or presence. Instead, it would express itself through stability, continuity, and resilience. A reality that seems slightly too well behaved, too consistent across time and scale. If an advanced civilization had reached this stage, its existence would not be proven by what we see, but by what never happens. No catastrophic drift, no runaway instability, just a universe that quietly avoids extremes. The unsettling implication is that control at this level would look exactly like nothing at all. With attention shifted toward subtle influence, scientists have begun re-examining the past with different questions in mind, not searching for lost empires or advanced tools, but for discontinuities, moments where the record feels incomplete or abruptly altered. These gaps are common in deep time, yet their patterns matter. Geological history, for example, is marked by long periods of relative stability, punctuated by sudden change. Some of these transitions are well understood, driven by volcanism, impacts, or climate shifts. Others remain only partially explained. The data exists, but the causes are still debated. Uncertainty persists even after decades of study. Archaeology faces similar challenges. Human history is reconstructed from fragments, and entire cultures are known only through traces. The absence of evidence is usually attributed to erosion, decay, or limited sampling. These explanations are reasonable, but they also highlight how easily information can be lost. A presence does not need to be hidden to disappear. Even within recorded history, there are periods of rapid technological or organizational emergence that resist smooth explanation. Innovations appear clustered rather than gradual. Scholars caution against reading intention into this pattern, yet the clustering itself invites closer examination. Some researchers extend this curiosity beyond humanity entirely. Earth has hosted life for billions of years, yet technological intelligence emerged only once and relatively late. This could reflect rarity, or it could reflect survivorship bias. Previous attempts may have risen and fallen without leaving durable marks. From a planetary perspective, advanced activity need not leave monuments. Long-term optimization could favor minimal alteration, not expansion. Structures built to last millions of years might look like geology. Systems designed to dissolve could leave nothing behind at all. Absence does not imply non-existence. These considerations do not suggest a hidden narrative beneath history. They emphasize the limits of inference. The past is reconstructed, not observed. Every conclusion rests on what survived, not what occurred. This distinction becomes critical when evaluating deep time. If present-day observations hint at subtle, ongoing influence, then the question of prior presence becomes unavoidable, not as a claim, but as a possibility shaped by uncertainty. The same blind spots that limit our view of the past may also limit our understanding of the present. Any discussion of extreme advancement must also confront limitation. No system, regardless of intelligence or precision, escapes physical constraint. Energy sources degrade, information accumulates error, and complexity introduces fragility. Progress does not eliminate risk, it reshapes it. Long-term stability requires constant correction. The more finely balanced a system becomes, the more sensitive it is to disruption. Small failures can cascade if left unmanaged. Over cosmic timescales, even rare events become inevitable. Survival, then, is not guaranteed by advancement alone. Some theoretical models suggest that highly optimized systems may choose to reduce activity rather than expand it. Dormancy, dispersion, or self-limitation could be strategies for persistence. From the outside, such choices would resemble disappearance, not collapse, but retreat beyond detectability. There is also the possibility of internal exhaustion. A civilization focused on control and optimization may reach diminishing returns. Maintaining coherence could consume more effort than growth ever did. At that point, continuation becomes a question of cost rather than capability. These outcomes do not imply failure in a dramatic sense. They reflect the natural tension between complexity and endurance. If advanced civilizations exist or existed, their absence from obvious detection may not signal impossibility. It may simply reflect the quiet, precarious balance required to remain at all. The investigation does not end with proof or denial, but with a narrowing of uncertainty. Across frameworks, observations, and theory, the same pattern repeats. Advancement does not necessarily grow louder with time. It may become quieter, subtler, and increasingly difficult to distinguish from the systems it operates within. What once seemed like absence now carries a different weight. If scientists are only now realizing this possibility, it is not because something new has appeared overnight. It is because our questions have changed. The central mystery remains unresolved, not whether an advanced civilization exists somewhere beyond reach, but whether one could exist without ever announcing itself, and whether, in that silence, we would even recognize it if it already does.